All right, can people hear me okay? Actually, does this thing need to work? I'm actually not, I can't tell. Yeah, mic's on. Okay, so where we left off yesterday, well, first let me just tell you that in the next two lectures, what I'd like to do is just finish off this discussion of a dark photon coupled to a dark Higgs, because that'll allow us to touch on the scalar portal, which has some very rich phenomenology. And then we're going to pivot and talk about light dark matter models. And I'm not going to have time to give you an exhaustive summary of all the light dark matter models out there. I'm going to try to give you a bird's eye view and then focus on a few of the cases that are talked about probably most often within the literature and in the community. Okay. So where we left off, I'll give just a few minutes of recap here. Part of the motivation for thinking about minimal models that have not just a dark photon but a dark Higgs was to provide a dynamical explanation for where these mass scales could come from and help motivate different mass ranges that are worth thinking about. And so the minimal dark photon plus dark Higgs involved all of the ingredients that the minimal dark photon model had, but now we have a scalar state that's charged under this abelian U1 dark. Okay, so this is a U1 dark gauge theory plus now our HD state, which I'm going to just say this is, I'm going to just give it charge 1/2. We could give it charge 1. It doesn't matter under U1D. Yeah. Yes. Okay. Now, the motivation for thinking about this was that we wanted to construct a theory that could give rise to a dark photon mass through spontaneous symmetry breaking. I told you yesterday that motivated from considerations of supersymmetry at the weak scale, a lot of the model building focused on approximately supersymmetric dark sectors. I wasn't going to get into that and instead just summarize the primary non-supersymmetric pieces. Go ahead.
I know you said it doesn't really matter, but is there some reason for choosing charge 1?
No, there's literally no reason. It's totally arbitrary at this point, but it's a convention that'll help me later. Okay, and so we had a Lagrangian that included we had our Higgs with covariant derivatives to the A prime, and then we just included marginal operators. For the dark Higgs self-interaction, and then the key ingredient was to introduce a Higgs portal coupling that connects the dark sector Higgs to the standard model Higgs. And this is the only dimension 4 operator we can write down that does such a thing. Okay? And then the point is that for kappa less than 0 here, which is actually automatically the case for a particular linear combination of scalars and supersymmetric models. Here it's just a choice. This means that electroweak symmetry breaking implies U1 dark breaking, okay? Right, so if the standard model Higgs takes its VEV, then we pick up a negative soft mass down from the weak scale by kappa that drives U1 dark breaking. And so then the schematic picture for the mass scales is one where We have the weak scale up here, and then we have the dark sector mass scales, MA prime, which are down by root kappa times the weak scale. Sorry, I should write that larger. Okay, so this was this basic motivation for explaining a massive dark photon through spontaneous breaking, and here we can even tie it to the weak scale where we generate a hierarchy that pushes these dark sectors into the GeV scale or smaller range, assuming that the mixing with the standard model is small. Okay, that's where we ended yesterday, I believe. And this is the setup for writing out the more complete dark photon plus dark Higgs model. So the full Lagrangian just to write it. So we have our dark photon kinetic term. So first, just the ingredients, right? We're going to expand about the U1 dark breaking vacuum, okay? So expand around H dark equals V dark. I'm sorry, this got cut off, but we're expanding around the VEV of the dark Higgs. We have a degree of freedom. We have a massive A prime, and we have a real scalar H dark. And I'll write that again up here, okay? Okay, so those are the kinetic terms for the dark photon, expanded about this vacuum. Then we have kinetic terms for the real dark Higgs, in this case. If you catch me writing H prime instead of H dark, it's because I use both notations. I'll try to be consistent. Yes. This actually motivates maybe just using the prime notation. Because it actually draw, you can actually tell there's a prime there. So I'll make that a prime. And it's easier to write. Okay. Okay, so then we have the interaction terms, which we have our interaction term of the dark photon, the electromagnetic current. There's, of course, the A prime Z mixing pieces, which we typically ignore. And I'll write it down on the bottom here, and then I'll push this up to the top in a second. We also then have a set of additional interactions that involve our new ingredient, H prime. So we have a coupling. So this is V dark of the dark Higgs to the dark photon. This is the most important term. And then we have some additional pieces that I'll write for completeness. And then there's, cubic term. Oops, squared over V dark, H prime cubed plus MH prime squared over V dark squared H prime to the fourth. Okay? Okay, so that's the full Lagrangian of this minimal model. Plus one important piece that I've run out of space to write. Okay. So let's send this up. Okay. Plus, this is actually just a reasonable way to label this board is, let's not forget that part of the motivation, at least in this particular model, was to include this coupling between the standard model Higgs, and I'll just write it like this, involving the Higgs portal. Yeah.
Did you say that this was happening when electroweak acceleration was happening?
Yeah. Yeah. So let's, if we want to be complete, we can write this expanded where we just put that in. So we can put V plus H squared, and then V dark plus H prime squared. But just remember, this descended from the operator H dagger H dark dagger. This came from that operator. Okay? All right. So let's just talk first about the physics of the dark Higgs in the absence of this term, if we can imagine that kappa is very, very small, which we were. But then let's come back and include the effects of this kappa. Okay. All right. So the first case, let's just for simplicity assume that MH prime, the dark Higgs mass here, is heavier than twice the A prime mass. Okay. So in that case, note that we have this trilinear interaction here. And so if we have a dark Higgs, there's then going to be a decay to dark photons, okay? And of course, recall that the dark photons themselves can come back to standard model fermions, right? So this provides a decay channel for the dark Higgs. Go ahead.
Just a quick one. You said we're assuming kappa is small, but is it small and negative? Does it have to be negative?
So to trigger electric symmetry breaking, it needs to be negative.
Great. Okay. So that's our assumption.
Yeah. Sorry, to trigger U1 dark breaking. I think I misspoke. Okay. It's worth saying that in the supersymmetric dark sector models, what always happens in practice is if you have vector-like pairs of supersymmetric matter, and there's always one linear combination that does have a negative soft mass direction. Here I've just discarded everything except the linear combination that matters. All right. Now, for reasonable values of, so I mean, note this is controlled by MA prime squared over VD, so this is of order the mass scales in the dark sector. So this decay, when it can happen, is typically going to be prompt. And then whether or not you come back to standard model leptons will be determined then by the lifetime of the A prime. Okay. And then if we go to the regime where we're less than twice the A prime mass, things get interesting. In this case, we start with the Higgs. There's actually a couple of different things that can happen. One possibility, depending on this mass ratio, is we just go through off-shell A primes, back to standard model leptons, or mesons, etc. Or we could also have there's a range of masses where one of these could be off shell. Say this one. Right, so then you have leptons followed by an A prime, and then maybe the A prime travels some distance and then it decays back. Okay, so that's, or as you get smaller in dark Higgs mass, there's a triangle graph that can be important, where these are A primes in the loops. Okay. All right. So the point to make here is that this, quote unquote minimal dark photon model that realizes spontaneous U1 dark breaking, this dark Higgs introduces quite an array of phenomenology on its own. If it can be produced, there's a number of different decay channels for coming back to the standard model. So it radically changes the physics. That's the main takeaway here. Now, Natalia just got started today, but I think in the context of B factories, this may be mentioned, because this is the kind of physics that people look for in lepton colliders, like B factories, previously LEP, where the environment is otherwise fairly clean. And so you can actually look for these kinds of final states with some degree of precision. Okay, now this is what happens just from the interactions implied by the presence of this charged dark Higgs. But there is this Higgs portal operator that was one of the principal motivations, or at least one of the motivations for thinking about how you tie the electroweak scale to the dark sector scale. And that's going to introduce some interesting physics. Okay, so in particular, right, so just writing it, this kappa H dagger H dark. This implies that we have the canonical Higgs portal operator. So using the notation of our previous Lagrangian, we have a term 2 kappa V dark H prime, right? So this is the dimension 3 operator, and this is the mass scale associated with it. And then we have our kappa H prime squared. Right, so this is the standard Higgs portal, as it's often written in the literature. And this implies that we have dark Higgs, standard model Higgs mixing. And that's a big deal. And the mixing angle is roughly kappa V dark V over M Higgs squared minus M prime squared, which for the range we're considering for small kappa here is kappa V dark over V, which is much less than 1. It's a very, very tiny, it's a very small mixing angle for provided kappa is small and you have this hierarchy of scales. Now, what this means is that, and I'm not going to go through and diagonalize the mass mixing here, okay? I want to just summarize this so that we have time for the light dark matter. So in the mass diagonal basis, H prime couples to the standard model like a standard model Higgs, but with theta suppressed couplings. Okay? So all that you know about how the standard model Higgs couples to standard model fermions and gauge bosons, namely those couplings are proportional to mass, you can recycle all of that and understand the phenomenology of this minimal dark photon plus dark Higgs, coupled to the standard model now with a Higgs portal operator, as now you have a new scalar with theta suppressed couplings that are otherwise just like a Higgs. But of course now this scalar is quite light, and so that can change things quite radically. So there's a range of rich phenomenology here. I'm just going to summarize some of the salient features of that. Okay, so for example, just to name one, so if you go to high energies and you think about producing the Higgs at the LHC, there's a channel that involves Higgs decays to dark Higgses, and then depending on how those dark Higgses decay, which now will involve a competition of these couplings plus the tree-level couplings of H prime to standard model fermions, you can look for a wide variety of rare Higgs decay modes in that context. And a number of those searches have been carried out, and they set constraints on this coupling kappa. At lower mass, though, the strongest constraints come from rare meson decays, decays of kaons and B mesons in particular, that violate flavor. Go ahead.
Just going back a tiny bit, talking about this dark Higgs standard model Higgs mixing. Should the true vacuum then be thought of some combination of the Higgs Vev and the dark Higgs Vev?
There's a small mixing. So when you diagonalize the mass matrix, you're doing a rotation or a field it's a rotation in this case of the standard model Higgs and the dark Higgs. So it's like it's a small adjustment.
Gotcha.
Okay, so for example, we can have, if you consider the following diagram, see if I can draw this correctly. So these are the penguin diagrams. So we have charged bosons here. So I'll start with S bar quarks, and then we have loops of U bar, C bar, or T bar. Right, and now we have an H prime coupling to standard model fermions that have a coupled to mass, but there's a theta suppression here. And we can have mesons along for the ride. So this implies, for example, K plus minus decays to pi plus minus, and then an H prime. Also, neutral kaon decays to pi 0 H prime. Okay. Now in practice, if what's sometimes done when people present constraints on these models is they will assume that only the Higgs portal operator is important, and will ignore any couplings, say, of a dark Higgs to a U1, because you can, in principle, consider a minimal model like that, where you just have a real scalar mixing with the Higgs. So that's not uncommon. Now, when that's the case, then in the regime where this decay can happen, note that this requires that the dark Higgs mass would have to be smaller than the mass difference of the kaon pion, so this is at low masses now. In that regime, this dark Higgs will typically be invisible as far as collider experiments are concerned, just because the couplings that controls decay are now like electron Yukawas, which are tiny. Okay? So the searches that constrain these are K goes to pi plus invisible. But please remember that in even slightly more complete model like this minimal dark photon plus a dark Higgs, these other decay modes can be important and can change the picture. So at slightly higher masses, there's an analogous process that involves, let's see if I draw this right, B quarks. And so this implies B plus minus decays to kaons. Okay. And this is something that, depending on what the H prime does, can be searched for with high precision at LHCb, for example, the Large Hadron Collider. Now, what's typically assumed is if you just have the Higgs portal and nothing else, then you would expect that in the mass range where this happens, where this can happen, a good fraction of it has the dark Higgs mass above the muon threshold, in which case you can have a prompt decay of the dark Higgs to mu plus, mu minus. And that's actually the mode that I think people search for with the highest degree of precision. Yeah?
Could this be a potential solution to the B anomalies?
So this class of models more broadly is used for, not specifically this one, but it's let's just call this like a piece of a broader class of models that have additional states that couple to the Higgs. Go ahead.
Is the reason you stuck the dark Higgs there because you want the top mass?
Yeah, so the loops that dominate here are, what typically dominates is the top. Sorry, not what typically. What dominates is the top. Okay, so all I want to say here is that within it, under the assumption that the dark Higgs U1 vector types of interactions can be ignored, either because you're thinking about a model with just a dark Higgs and nothing else, or because these couplings are tiny, existing constraints for B decays to kaons plus mu minus pairs and kaon decays to pions plus invisible suggest, so I'm not going to name all the experiments. I'm just going to refer to them as experiments. And I think there are some plots that Natalia might show, potentially, that theta should basically be smaller than a few times 10 to the minus 4 for MH prime less than a few GeV. Okay? And I keep saying this, I probably sound like a broken record. Just be careful, though, when you look at constraints on these scenarios, because there are often these hidden assumptions. Okay. Now, there's one more thing worth pointing out about the utility of the dark Higgs once you imagine you have it around, which is if you have any dark sector matter, this offers an easy explanation for how the mass scales for that matter could arise in the vicinity of the A prime mass or the dark Higgs mass just through Yukawa couplings, okay? And just to give an example of that, so I'm just going to call this the U1D dark Higgs model. Plus matter. And now we're really talking about full-blown dark sectors here. All right, because now we're talking about sectors neutral under the standard model, but now they've kind of got all the moving parts of the standard model. We've got new gauge forces. We've got Higgs-like states. We're going to have matter states. In principle, we don't know. But the most general possibility isn't going to be too far removed from that. And so in a simple example would be, and this is not the most minimal example, but you could have vector-like fermions, vector-like under the U1 dark charges, fermion pairs. And just to write out a matter content, so we can have, I'll label it psi plus 1, psi minus 1. So these carry plus minus 1 U1 dark charge. And we can imagine, if we want to actually make a sort of dark sector look standard model-like, you would actually introduce something that's actually chiral, or at least can be thought of that way. So this would be plus or minus 1/2 U1 dark charge. Okay. And that implies that we can have Lagrangian interactions that include things like y, h dark, psi minus 1, psi plus a half, call this the half, y minus a half, h dark conjugate, psi plus 1, psi minus a half, plus dot, dot, dot. Right, so in this simple vector-like model, which actually I've written to be, I'm imagining actually that there's a chiral discrete symmetry that forbids the vector-like mass terms. In this case, dark Higgs, the U1 dark breaking and the dark Higgs taking a VEV would introduce actually Dirac-like mass terms in this case. So this minimal Lagrangian implies massive Dirac fermions at a scale m psi of order y times v dark. So again, less than or equal to a few GeV. Right along with everything else. Okay? All right. Questions? There's more to say about the generation of mass here, but I think this is sufficient for now. Go ahead.
Are there constraints that you could put on the dark Higgs VEV itself, or just the mixing between the Higgs and the dark Higgs?
Well, I mean, in these minimal models, you can sort of swap the mixing for a combination of the VEV and kappa.
But it's those two parameters that.
But it's the mixing angle that is constrained as a function of mass, as a function of dark Higgs mass. Okay. So that's all I want to say about dark photon plus dark Higgs. And now we've started thinking about what happens if you have matter states in a dark sector. And that's the perfect jump-off point for thinking about the minimal dark matter models in the context of dark sectors. Okay, so what I want to do for this, because I know that some of the previous lecturers also talked about dark matter models like the classic WIMP. I think there were also discussions of different kinds of explanations for the origin of dark matter that don't just involve canonical thermal freeze-out. And it can kind of seem like there's just this huge array of possibilities. And there are, okay? Especially when you're thinking about a dark sector. I like to hang all of these different models on a conceptual scaffolding that's built around very basic questions about where dark matter comes from. And I want to just summarize that for a second, just to put all of these different models kind of in context. You know, axions, WIMPs, forbidden annihilation, you know, blah, 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 right? So on the one hand, we have a pretty good idea of what the energy density of dark matter is now. And we have a lot of evidence that it doesn't really carry any entropy. It's non-relativistic. But on the other hand, we have a lot of evidence that the early universe originated from a hot thermal era with temperatures at least as large as an MeV, okay? We've never directly seen temperatures like that in the sky. The best we can do is see like electron volt scale temperatures from CMB recombination, but Big Bang nucleosynthesis gives some pretty compelling evidence that the universe was hotter than that. So, very zeroth order question. Was dark matter ever in thermal equilibrium with us? It's just the first blanket question you should ever ask when somebody talks about a dark matter model. Because if it was, then you're guaranteed just from that fact alone to have some relic density of dark matter, right? There's just a fall off the log easy explanation of where at least some fraction of the dark matter can come from. So for this, I have a little bit of a flow chart here that I want to get through quickly. I'm going to erase some boards here. Let's see, where is that one? Okay. Sorry, I'm going to need some board real estate for this. So I'm going to. Okay. All right, so what I consider to be one of the most kind of important questions to ask was DM, dark matter, ever in thermal equilibrium with us? Okay. Now, what has to happen for this, for GeV scale scenarios in particular, is that this is going to occur when the rate of interactions that exchange dark matter with standard model degrees of freedom. And these I'm going to just parameterize with some G dark squared times the mass scale in the dark matter sector. That's typically how these work out. These rates parametrically can always be put in that form. When this rate is larger than Hubble at some era. Okay. And at least for GeV scale states, this implies that this G dark needs to be larger than about, well, it needs to be larger than MdM over M Planck. It's kind of the parametrics of this, which is about 10 to the minus 9. Okay? So that is to say, it doesn't take a very large coupling to expect that dark sectors are going to equilibrate with the standard model in the early universe. Okay? This is definitely on the small end of what we've been thinking about. All right. So one possibility here will be the yes, and I'll go over there for that. The other possibility, of course, that I think you've heard about already. So if this doesn't happen, then you really ought to be wondering at a basic level, okay, fine, so it doesn't come from the thermal early universe, so where did it come from? It's got to have some other entirely different mechanism. So it's a little, I mean, it's a little cheeky then. It's just, so just go back to the basic question. How was DM produced? And there's sort of two classes of models that people typically use in this context, which is you either rely on initial conditions or and I'm going to be a little glib with the term initial conditions, okay? Because we have some evidence that we have some vague clue of what might have been happening in the very early universe if there was an era of inflation. And so initial conditions could be inflaton dynamics. But the point here is that after inflation, there's some initial condition of the universe. And we could just say that dark matter emerged with its density that we see today from that era. And it was basically baked in, okay? And there's a wide range of interesting models that fall into this case. So the QCD axion, morally, is one. ALPS, more generally. Primordial black holes, etc. You can also have other types of primordial relics that have late decays, where their abundance is baked in the early universe. And I'm just going to consider those to be initial condition explanations. But there's another interesting class as well, which is you don't use, they're admittedly sensitive to the initial conditions, but instead you use ultra-weak couplings. Ultra-weak contact with the SM. And so even though you don't equilibrate with the standard model, you have some amount of energy density and entropy that can leak in over time. Okay, and you basically, for parameters much smaller than these parameters, you can bake in an appropriate amount of dark matter density Again, this is sensitive to initial conditions. So these scenarios, you typically imagine that the initial condition is you have no dark matter, and then you allow a slow leak in of the thermal bath to produce it. These go by the terms freeze in, and there's a range of freeze in models. Actually, sterile neutrinos are a bit like this as dark matter candidates, etc. So there's a range of models like this, some of which you've heard about in this series. Go ahead.
So for the ultra-weak contact, at some scale, it's going to be in thermal equilibrium, right? Even if that's kind of at the inflationary scale?
No, because actually the relevant time scales are shorter as you go to higher and higher temperatures. These ultra-weak models have the property that typically the abundance is dominated at late times. Okay. So what about the case where the interactions are not wickedly small, so that you do expect equilibration to occur? Okay, so then you want to use this second clue that we get from experiment, which is that dark matter doesn't seem to carry much entropy. Okay, but if it descends from the early universe, it had entropy at some point, so it's got to go somewhere. So where does it go? Now there's sort of two options here. Either the entropy ends up in our degrees of freedom, or it stays in the dark sector. And the point here is that if it stays in the dark sector, for these light dark matter models, you very quickly run into trouble in those kinds of cases, from measurements of N effective, so essentially CMB measurements, Big Bang nucleosynthesis, large-scale structure formation inferences. Those scenarios tend to be tightly constrained for these light dark matter models. Okay? So, but for completeness, let me just write this out. I think you've heard about some of these constraints also, maybe last week. Please say no if that's not the case. Okay, so this arrow will connect to that arrow when I move it up. So in the yes case, so where did the DM entropy go? Punchline here is that the state in dark sector is tightly constrained for light dark sectors. So often in tension. With CMB, EBN, and large-scale structure. Okay, so that means that if we're going to be thinking about this, the entropy goes to the standard model. So how? And here we have, again, kind of two logical possibilities. This either happens relatively directly, or it happens through far more indirect means. And this is where you end up with this kind of, very interesting landscape of possibilities, okay? Some of which have been talked about. So in the indirect direction, which have already been discussed by some of the lecturers in previous weeks, so indirect. Typically, the way these scenarios work is you have dark matter annihilating to other dark sector states. I'm being schematic about this. So dark matter goes to dark sector. Dark sector, this would be a minimal possibility, plus your dark sector state then going back to the standard model. Or variants of this. So for example, it doesn't have to be 2 to 2. It can be 3 to 2, for example. You have different ways of carrying this out. So secluded dark matter falls into this category. So now, when I say secluded dark matter, I mean that's a term that you'll often see in the literature that refers to a broad class of scenarios like this. I think SIMPs have been discussed, possibly elders. I don't know if that was discussed in a previous lecture, etc. Forbidden dark matter is an example of this. Again, this is a name for a DM scenario. Okay? So broad category of models like that. Now they tend to have this property that the dynamics controlling entropy transfer and freeze out lives in the dark sector, not in the couplings to the standard model. Now then there's the direct path. And the direct path is what you'd guess. The classic WIMP falls into this category. And light-dark sectors have their own direct path, as you can probably guess by now, just from these minimal models we've been talking about. Go ahead. Yeah. DM goes to dark sector, dark sector. So in this case, this transfer is happening just directly in some primary interaction to the standard model or variance. I drew it as 2 to 2. But you can have scenarios where you have co-annihilation, so there's other degrees of freedom in the dark sector that are helping that along. You can have semi-annihilation. Point here is the classic WIMP is an example of this. And the sub-GeV dark sector models can realize relics that utilize this path as well. Now, again, so there's a rich landscape of possibilities for dark matter. This is just a way that I like to hang them all in my head. And I'm going to talk primarily going forward about this sort of direct entropy transfer class of models, largely because they tend to be the most predictive. These are scenarios where the relic abundance is dictated by interactions with the standard model relatively directly. And that makes it kind of interesting from the point of view of experiments. Because then when experiments go off looking, there's at least some motivation for particular ranges of interaction strengths and mass scales to look for new degrees of freedom that you can just derive from dark matter density. Okay, so the main virtue here, I just said it. So these are economical and they're predictive. And that's why I'm going to primarily discuss them going forward. Now, again, I'm focusing primarily on, I'm doing light dark matter here. So there's more to the story than this. When we think about light dark matter, let's see. This didn't quite line up, I'm sorry, but anyway, you see the pathways are, it's fine. I think you get it. Okay, so if you think about light thermal relics more generally, there's a couple very important high-level points that kind of push models of this form into the dark sector category, okay? There's a reason when we talk about light thermal relics, they tend to all be dark sectors. So the first, maybe I should reorder these. So one obvious one is that if you're thinking about light states that couple to the SU2 weak interactions, so if they have standard model charges, and they're below mz/2, those are hugely constrained by LEP, by previous E+ E- colliders. So the whole idea of light thermal relics that talk to SU2 directly is just sort of almost dead on arrival, just from this generations of E+ E- measurements that were producing billions upon billions of Z bosons that could in principle decay into such states. Okay, so already you should be thinking about dark sectors if you're thinking about light thermal dark matter. Now there's an important experimental fact that's worth highlighting, second important fact that applies to light-dark sectors, and this concerns the CMB, which has been measured with exquisite precision and is relatively well understood at this point. So here's the point. And I'm sorry if a previous lecture went over this particular point regarding light-dark matter, but on the one hand, we're thinking about GeV scale. So I'm going to draw a picture where I've got, you can see this line, okay? I'm going to put temperature on this axis. So that means time is going to go down. So time in the early universe goes down, lowering temperature. So we have an era of freeze out up here. For the scenarios we're talking about, that's typically going to be up in the MeV scale or larger, especially if you don't want to have to worry about any sort of non-trivial physics affecting BBN. And then we have the era of recombination down at the electron volt scale that CMB is sensitive to. And the point here is that residual annihilations of this direct type, although honestly this applies to even indirect annihilation, residual annihilation, even after freeze-out, distorts the CMB power spectrum, or at least it can distort the CMB power spectrum by a measurable amount. It does that by injecting energy into standard model degrees of freedom, which can then reionize atomic hydrogen. Okay? So this implies possible CMB distortions. Okay? And there's a specific constraint that this implies on the annihilation cross-section at electron volt temperatures compared to the annihilation cross-section that sets freeze-out. And this constraint is surprisingly strong. I mean, to my mind, this is one of the most impressive constraints that can be derived from early universe cosmology measurements and inferences on dark matter. And it basically is that the annihilation at temperatures of order electron volt, it's usually framed divided by the mass, needs to be smaller than a few times 10 to the minus 11. And I'll put this in units that make a little more sense in a second. If you were to put in a cross-section normalized to the typical freeze-out cross-section of a few times 10 to the minus 26 centimeters squared, centimeters cubed per second, you already start running into tension with residual annihilations, assuming temperature-independent annihilations at the sort of tens of GeV scale. Okay? So the punchline here is that if you have an annihilation process that gives you the right Rayleigh density that's independent of temperatures, you're going to run into CMB distortions that are measurable as you lower the dark matter mass below tens of GeV. Okay? Now, by the way, I mean, these constraints have been around for a while, and it's one of the reasons why light thermal relics didn't get a lot of attention years ago, okay? This kind of discourages thinking about light thermal relics that have this sort of temperature-independent characteristic in their cross-section, in their annihilation cross-section. Now what this tells you, though, just to summarize, is that somehow this needs to be much smaller than sigma v at freeze out, which is typically of order a factor of 10 or so below the mass scale of the dark matter. Now, it turns out this is not that big of a deal from a model building point of view. How does temperature dependence work its way into an annihilation cross-section? That happens, for example, if the annihilation cross-section isn't S wave, it's P wave, and then it just has velocity dependence. And then as you go to lower and lower in temperatures, that cross-section is going to get suppressed by temperature. So it's not a big deal, but it is really important because it singles out the kind of class of light thermal relic models that make sense to think about, at least the ones that are experimentally viable. Okay. Now there's a third important point about light thermal relics, which is that if you're not careful, or if the sector is not careful, unless it has some indirect way of depleting its entropy, the annihilation rate or its cross-section for getting back to the standard model can easily end up being too small. And then you end up in a situation where you end up with too much dark matter at late times. This actually provides a hint that if you're going to think about light thermal relics, you should be thinking about dark sectors proper, where you have dark matter with its own interactions, et cetera. And where does this come from? This is, I'm not sure if this was in the previous lectures, but there's this, people often refer to it as the Lee-Weinberg bound, right? If you just had a WIMP that interacts through the W and Z, then as you go to lower and lower masses, the cross-section decreases, and then the relic density goes up. And eventually you just can't, you get too much relic density at too low of a mass. Go ahead.
Really general question about dark sectors. So we know what our energy budget is for the dark matter, but every particle in the dark sector is going to contribute to that energy budget. So what distinguishes like what we call dark matter and the other dark sector particles?
The states that are stable are dark matter. Yeah, so like in the minimal model, so like dark photon plus dark Higgs, nothing there is stable unless things are very, very light, in which case they can be cosmologically long-lived. If you have matter states, especially if you have fermions and you have any discrete symmetries, accidental symmetries left over, then you typically will end up with one or more lightest states that are going to be dark matter candidates. So that's kind of a trivial outcome of very basic models. Okay, so just to summarize this point, if you have, because again, this motivates thinking about dark sectors in the context of light dark matter. If you are going to have a direct channel to the standard model, this rate goes like, the annihilation rate goes like MdM squared over the mediator mass to the fourth. And so satisfying sigma v, and I mean, this is a statement that applies to very minimal models. There's ways around this. This implies that the mass of your mediator cannot be too heavy. And in particular, for light dark matter, that mediator mass shouldn't be too far removed from the dark matter mass scale, okay? So again, turning this around, if you're going to think about light thermal dark matter, you should be thinking about dark sectors, which naturally have interactions that are not too far removed from the scale of the dark matter itself, from the scale of the dark sector itself. Okay, so what is the simplest dark sector dark matter model that builds on our dark photon plus a dark Higgs if we want to include it? So let's write that down. Smallest number of degrees of freedom, yeah. I mean, that's a simple-minded notion of simple, and it certainly doesn't work for the standard model, but we're going to employ it here because that's what most people mean when they say simple. But for pedagogical reasons, it just means there's fewer moving parts I have to talk about as well. Okay, but I'll refer to this as our example one. So the simplest. Dark sector. DM. And this will comprise, so we'll use a dark photon mediator. Plus a Majorana fermion. Okay, and I'll talk about UV completions of this shortly, and by shortly I mean tomorrow. So this is a minimal model that, all of its mass terms for the matter sector are going to be technically natural. If it's just a U1, you don't have any issues with naturalness either. And it's pretty minimal in terms of numbers of degrees of freedom. And because of that, its interactions are going to be largely just dictated by Lorentz invariance. And you essentially have like one kind of interaction you can write down involving the fermion with the mediator, and hence essentially one kind of interaction that you can write down involving the standard model and the dark matter. Okay? And that is that our interaction terms in this minimal model, let me give these names. So we've got we've got A prime for the dark photon, and then we'll have psi be the fermion. In the interaction terms, we'll have what we've been writing down multiple times before. We've got the dark photon coupling to the electromagnetic current. This is coming from the kinetic mixing, which I'm not writing out explicitly. We've diagonalized it away. And then we've got a coupling of the dark photon to this fermion. And it has to couple to some kind of current involving the fermion. Now, as some of you probably know, if all you have is a Majorana fermion, you can't write, that's massive. You can't write down a conserved current, but that's fine. In the context of a massive vector, massive vectors can couple to non-conserved currents, no problem. And in fact, that's the only interaction allowed by Lorentz invariance. Okay? So the dark current here has to be psi bar gamma mu gamma 5 psi. That is the only thing that you can write down. Now, I will emphasize, though, that this is in 4-component notation. So if, frankly, if you're talking about Majorana fermions, in 4-component notation, you would take, I'm sorry, I shouldn't do this. I already called that psi. Let's not ruin our notation. So I'll put psi here, and I'll call that psi 4-component. Okay? And the point here is that this is just equal to psi dagger sigma bar mu psi, where this is the Pauli matrix. These are Pauli matrices. Okay? So this is the 2-component notation for writing down the gamma mu gamma 5 chiral current in 4-component language. But if you're talking about a Majorana fermion, you might as well just talk about a single 2-component Weyl spinner and not make things too complicated. Okay, this is the only thing that you can write down allowed by Lorentz invariance. Now, I am going to UV complete this model in a way that will give you an explanation for where those kinds of interactions come from. You're not used to doing this, right? You're not used to writing down couplings of Majorana fermions to vectors. Normally, you have vectors coupling to Dirac fermions, okay? The way that these models arise, like as effective theories, is you have a Dirac fermion where you spontaneously couple to a U1, you spontaneously break the U1, and in the process, you also break the global U1, okay? So the mass matrix in general splits the states into Majorana fermions. And these are the kinds of interactions you get. And the lightest such state will have a Majorana coupling to the massive dark photon. So there's very simple UV completions. We'll get to that. Those are called pseudo-Dirac models. Go ahead.
I wonder if there's a reason why it's better for a UV completion to have Dirac versus Majorana fermions.
If you want to have a fermion in a simple way coupled to an abelian gauge group that preserves gauge invariance, it needs to be a Dirac fermion. Again, once we break the U1, we can do more interesting things. And this is the simplest kind of effective theory you can get out of that. Okay. So very simple, almost trivial model. It'll have equally simple UV completions that we'll get to tomorrow. But the physics of this is very simple. There's essentially only one thing you can do to come back to the standard model. So now psi has an A prime mediated annihilation to standard model degrees of freedom. So that's the process that would set the relic density in the early universe. This cross section, of course, scales as epsilon squared alpha dark m psi squared over ma prime squared. And it has a factor of v squared, okay? This is velocity. Okay, so for a Majorana fermion annihilating to standard model fermions through a vector, it's going to be p wave. It's the only thing allowed. So that'll turn out to be important for CMB. What's typically done in these simple models, though, is in this case where the relic density is controlled in this very constrained way. There's a particular combination of parameters that are often shown. So if you want this to be equal to the thermal freeze-out rate, then that implies that the combination, which is called Y canonically, epsilon squared alpha dark, and it's presented as a dimensionless variable. This needs to be approximately equal to 5 times 10 to the minus 14 m psi over mev squared. Okay? So basically, when the underlying parameters satisfy this relation, you're going to get roughly the right relic density. Go ahead.
Could you repeat why this has to be P, please?
That is just a property of calculating the annihilation cross-section for a Majorana fermion which can only couple to a vector this way. So that's just a property of the model. It's not like a choice. It's not like Majorana fermions don't have S-wave annihilations through a vector mediator. Okay. So let's actually just look, because yesterday we talked about, sort of typical values of epsilon and alpha dark from one loop mixing and so forth, right? So the mass scales we're thinking about here are GeV scale or less, so sort of we'll bracket them in the MEV to GeV range now, and we're going to bracket it on the lower side at MEV because below an MEV, dark matter that's a thermal relic can be problematic from the point of view of BBN in ineffective measurements, okay? So we're just going to bookend it down there. But let's put in sort of typical values of epsilon and alpha dark for mass scales in this GeV range. Okay, so let's set m psi prime. I'm going to put these things kind of all roughly in the same ballpark. When constraints are shown, there's often like particular ratios of mass close to order 1 that are chosen. But at least here, this implies that alpha dark epsilon squared is about 5 times 10 to the minus 8. Okay, so we were imagining, say, one loop epsilons. So 1 loop epsilon implies, let's just put in the 10 to the, so 10 to the minus 3 is a fairly typical value that's considered for epsilon, so that gives you epsilon squared 10 to the minus 6. We could put in an alpha dark, that's a few 10 to the minus 2. And that's is totally compatible with what you would expect from just getting the freeze-out density. So the punchline of all of this is that I often put sub here because this works to lower masses. So GeV scale dark sectors with 1 loop to 2 loop scale mixings and in this case, the mixing here is just the kinetic mixing, epsilon. Naturally give viable thermal dark matter, thermal relic dark matter. With sort of roughly the right abundance. Now, this is not as striking as the classic WIMP miracle. Although, the WIMP miracle doesn't work like, you kind of have to engineer it a little bit, but parametrically, weakly interacting particle at the weak scale is sort of roughly gives you the right cross section, and then you can kind of tweak it from there. If you put in 1 loop couplings at the GeV scale, likewise, you sort of roughly land in the right ballpark for getting the observed density that we see just from these naive estimates. But of course, you can tweak it. You could choose larger epsilon, which case you would have a subdominant dark matter component in this way. If epsilon were too small, then you'd run into the fact that you would overclose and you'd have to come up with some other explanation for how dark matter would annihilate away. But the punchline here is that the dark sector framework kind of naturally provides the key ingredients for light thermal dark matter. So we have motivations for thinking about the GeV scale underneath the weak scale, and we have motivations for small couplings. And those two combined kind of land you in the right region for a viable thermal relic. Now I want to stop there. Are there any questions? Go ahead. All right, so tomorrow I'm going to continue with these minimal dark matter models, just being very specific with the models. We can talk about, I didn't finish off saying how this works with the CMB. The punchline, of course, is that it's P-wave. And then we'll move into their UV completions. You'll see they have some interesting phenomena. The UV completions of these have some interesting phenomenology. And then I'll probably try to connect this to the most often discussed minimal models that are relevant to dark sector experiments.
Just a quick little announcement. You may have seen already my copy that the group photo is there, and there's a key to who is what person, and if you can find yourself and write yourself down, so you will be properly identified. That would be good. Or if you have some alias stuff, that's done. Have a good lunch.
Yes.
So I was referring to the dark photon dark Higgs model where you have the U1 value. Let's say I consider the RT universe cosmology, I draw it from cosmic rays. In this case of
With the dark breaking of the U1?
yeah.
Would you do that with, would you actually do that with an abelian group though?
Abelian case, sorry, the cosmic rays.
Yeah, so the thing is that the breaking occur. I mean, usually the way that works, right, is that you break the U1. If you break the U1 early enough, then you can make these the defects can have like an appreciable density. I thought that when the breaking is relatively low mass.
But this is at electroweak scale. Breaking that.
Well, sorry, if you include finite temperature corrections, electroweak symmetry breaking will happen, but you actually have to wait a little while
To
before
get
the
wave
U1 dark
for
breaks.
okay.
That's right. Yeah. Yes, it was. Yes, I'm. There's still the problem of me writing too small.
Take a look at this. Try to read this from the back of the room.
Yeah,
So that's
it's a bad habit.
when you write big, it's good. But then I think just sometimes it gets really tiny. So yeah, just something to work on.
That's like
I don't want to be like I have a problem with your handwriting. The bigger the better, I think.
yeah. My annotations, when I have this problem anytime I lecture on a board, is that if I try to include afterthoughts to define the notation, if I haven't done it carefully, and it ends up being microscopic. So
Interesting. That's interesting. I know someone who does this verbally. That like if he's saying something that he is thinking of as parenthetical, he lowers his voice so that it's hard to.
so in my case, I just write tiny. It's like
It's interesting how the brain.
I don't even notice it too. But now that I'm looking, actually, this is pretty consistent.
Yeah. It's interesting.
I got my velocity. It's like, yeah, in case you didn't know, this is
The
velocity.
annotations on like the diagrams, the letters on the diagrams.
Yeah, all right.
But yeah, they've been great talks. So thank you.
So it's supposed to be an MA to the 4 in the denominator.
God, yeah. If, yeah. Thank you.
So I just wanted to ask, so why is this limit independent of MA prime? on
It's not.
Okay, so are we
Oh,
assuming?
I'm sorry. So you mean this?
Yeah, this, yeah.
So sorry. The way you should read this. So what's happening here is sigma v is being constrained to be this value, right?
Right.
So what's often done is it's presented as a dimensionless as a constraint on a dimensionless parameter as a function of dark matter mass. So take this formula here, multiply and divide by m chi squared,
Right.
and you see the combination y appears there, and then you have 1 over m psi squared,
Yeah, okay.
and that's why it's written as a constraint that depends on m psi.
That makes sense. Yeah,
Okay.
with the MA. Okay.
Hey, so we're collecting C's from everyone here. This is like 80 of them. And potentially this will be on a shirt. If you want to add your
Tassi shirt. It's our Tassi
You
shirt
get
for the
only,
year.
you go only one. Okay. Maybe initials under.
Better than mine.
It's fine.
Normally I'd erase that top thing. I never actually write it like that, but
Thank you.
okay.
4 more.
Can I expect like the story that's being told here with like, this minimal model to more or less hold at the qualitative level when they go to like, say more complicated non-minimal models?
Yes, except that the UV completion I'm going to show, which is known as the pseudo-Dirac model, in the the supersymmetric context, you'll often get Majorana dark matter as your lightest state. And that's just because the fermions in the matter multiplets are just they're Weyl fermions. And in particular, what often will happen there is like you'll have like gauginos that'll be like the lightest states, and they'll naturally be Majorana, but not for the reason that I'm going to tell you in the UV completion. So I guess the answer is the low energy part.
Okay.
The reason, like the UV completions though, are varied. Okay. This is a common theme of EFTs though, right? And the path that I'm going to choose is actually not the path that you would encounter if you were to UV complete into a supersymmetric dark sector. Because I just don't think the lessons are really different. Yeah.
So I think like NA64 puts bounds like this, and then this is Babar.
Yep.
Whatever.
Yep.
And then I don't know. There's some bumps here and there. So like this would be the S wave freeze out, right? And then it's kind of
What is that last line you're drawing? This one?
I'm trying. This is freeze out.
Oh, yeah. So there's usually several freeze-out curves shown.
Yeah, and so I think this is what they usually do for S wave.
Well, oftentimes there's all of the models that are typically shown usually include an S-wave example, which is CMB viable if it's asymmetric. And then they'll include Majorana and pseudo-Dirac. And those are CMB viable for different reasons. And those they're not way up, they're only like slightly removed, right? And
I thought that was pretty close.
well, it's like a factor of a little less than 10 difference. So you're wondering about NA64 versus that?
Well, I think this is Babar, and then
Clo-
this
clo-
is NA64, and then this
Yeah,
guy I think is pretty close.
where these freeze-out lines are relative to the colliders depends on your choice of alpha dark. So there's a little a cheat that some people sneak into their constraint plots, which is they'll choose alpha dark to be small, like alpha dark of this. Okay, so this is chosen.
Random.
It's chosen to be conservative because if you make that hierarchy larger, the freeze-out curve okay, so if you make this hierarchy larger, so MA prime's heavier, these curves all go up. That's largely constrained. So if you go to the resonance region, the curves go, so MA prime equals 2 chi, the curves go down. Now they don't go down arbitrarily far because the resonance